So the talk is going to be divided into 3 parts. First, I'm going to give an overview of the situation, mainly on the complex numbers. Then we're going to move on to positive and mixed characteristic, where we are going to see what is still okay and what is not okay anymore. And then I'm going to conclude with a couple of questions that I think are natural and interesting enough. Yeah, of course, if anybody has any questions or something is not clear, feel free to interrupt me. Also because I'm not sure I can see the chat if the questions are asked there. All right, so let's begin with some notation first. So for me, R will denote an excellent DVR with the perfect residue field of characteristic P, which is always going to be positive, and fraction field big K. Now, a pair, in its most general notion, the most general notion is the data of XB, where X is a reduced pure dimensional G1 excellent scheme over a field over a DVR, together with a Q divisor B, usually effective, such that its irreducible components are not contained in the singular locus, and the adjoint divisor Kx plus B is Q Cartier. Most of the time, our pairs will always be normal or at the very least integral, so don't worry too much about things with many components. Anyway, I'll spell out all the hypotheses that we are working on each time, under each time. And a remark, which is going to be important, we are not requiring our space to be S2. So remember, S2 is sort of the algebraic version of saying that the Hartog's theorem, Hartog's theorem holds in complex analysis. So sections of the structure sheaf are determined in codimension 1. And these are very useful property because you can work with divisorial sheaves as if they are basically line bundles. But we are not requiring this, and this will be important. A scheme is demi-normal if it is S2 and it is at worst nodal in codimension 1, so either nodal or regular. And a family of pairs will consist of a pair XP and a flat morphism to a regular one-dimensional scheme T, such that all the fibers are pairs for every point on the base. All my family will always be over a regular one-dimensional scheme. So this is the easiest, sort of the simplest kind of families that one can consider. And for our purposes will be general enough. And when you have an R scheme over a DVR, I will denote by X sub small k and big K the closed and generic fiber, and the same goes for subscheme, coherent sheaves, etc. And I will always confuse between Cartier divisors and line bundle, but this should be okay. All right, so with this out of the way, let me recall you what the plurigenera are. So if you have a proper pair over a field K and you have a positive integer M, such that n times B is an integral divisor, then the M plurigenus of XP is defined as the dimension of the space of M tensor power of the canonical line bundle Kx plus B. So if you're familiar with this line of thought in higher dimensional algebraic geometry, these linear systems are the ones that carry all the information about the intrinsic geometry of the pair. And so their dimensions are sort of natural invariants to consider. So the starting point for us is this theorem, first proved by CU in the case of smooth families, and then generalized by Berson, Paun, and Hecom-McKernan to more general families of pairs, which states the following. So if you have a projective family of normal integral complex pairs, such that the family is nice enough, meaning either it's log smooth and with KLT fibers, or log smooth and LC general type fibers, or canonical fibers with canonical singularities, then these plurigenera are actually independent of the fiber for every M. So they are deformation invariant. So this is a nice result because it's telling you that sort of these canonical, pluricanonical linear systems behave very well in family. They deform. Couple of remarks. So this is really an extension theorem. So the invariance of H naught of a line bundle means that you can lift sections from a fiber to the total space. So this is really a result about surjectivity of this restriction map. And its proof, interestingly, it's very, very analytic. So it uses this L2 extension theory developed by Ozawa and Takegoshi. And this is the kind of analytic proof that you cannot recast in an algebraic language. So this is the only proof that we have in the general case, and yeah, it's an analysis proof. And besides being a very natural result to hope for, this has also quite important applications to the construction of moduli spaces for varieties of general type. So let's say a few words about those. So these are known as KSBA moduli, and you should think of them as a higher dimensional version of the moduli of weighted stable curves developed by Hassett. So the idea, one would like to start by saying, oh, okay, let's construct a moduli space for integral LC pairs of general type XP, where we fix some invariants like the dimension and the volume of the log canonical divisor. So if you start with those, which are the most direct generalization of a G greater or equal than 2 curve, you already run into some problems because these, from a moduli perspective, these pairs, this class is not very well behaved. This, for example, is non-separated. There are many, many examples where this can happen. And so the solution is to replace a pair by its canonical model. So remember, if you have such XB, you can take its canonical model, which is just defined as XC, where XC is the proj of this ring, which is the canonical ring of the pair. So if you start with a general type pair, this map will be birational. The canonical model XCBC will still be a pair with LC singularities, dimension n, of course, and volume V, but now we will also have more positivity on the canonical divisor. So this guy will be ample now. And these are one should really consider this because the main difference with the moduli of curves is that if in dimension greater or equal than 2, birational and biregular equivalents do not coincide. So this is you should take these as sort of the best distinguished representative of a birational equivalence class. So you want to parameterize those. So, okay, you say, okay, let's take the objects as XP log canonical models of dimension n and volume V, and then as families, we just take families of log canonical models in the sense introduced in the notation. And things are better now. The moduli functor S and V turns out to be separated, but it's no longer proper. And this is not really surprising. Already in the case of curves, this is true, right? You can have a smooth curves that degenerates to something nodal or something that has 2 components meeting transversely. And this is the reason one introduces stable pairs. So this is a bit technical, but we need this definition. So a pair over a field of characteristics 0, XB, is semi-log canonical or SLC if the total space is demi-normal, and when you take the normalization map and you let D bar in X bar be the preimage of the double locus, and B bar just the divisorial pullback of B, then you obtain a log canonical pair. So semi-log canonical is sort of the non-normal version of log canonical. Oops, sorry. And if you have a SLC pair which is projective and Kx plus B is ample, we will call it a stable pair. And a stable family will just be a pair with a flat proper morphism to a regular one-dimensional scheme T, such that one of these 2 equivalent condition holds. So A prime would be the fibers are semi-log canonical for all T, or a double prime X B plus XT is semi-log canonical for all T in T. And finally, you want Kx plus B to be pi ample. Now, This will come back again later, so please try to remember this equivalence A with A prime with A double prime. So this is a form of a adjunction or inversion of adjunction, but it's a very general one. And I'm assuming here characteristic 0 because this equivalence, as we will see, is no longer true in characteristic P. So with this notion of stable pairs and stable families, you can form a subfunctor of S and V, which we call S bar and V. And it's a result that has been established after, thanks to the work of many people, Collara, Consueco, McKernan, Shu, to name a few, that over the complex numbers, this functor of stable pairs is actually very well behaved. So it's representable, separated, proper, bounded, and it emits a projective coarse moduli space. So things over here are very nice. So what does Hughes' theorem or this invariance of plurigenera theorem have to do with the KSBA moduli? Well, if you remember, the idea behind the KSBA module is that you should not take, you should not parameterize varieties of general type, but you should take rather their canonical models. And Hughes' theorem implies some sort of functoriality of log canonical models. So, namely, if you have a XBT, a log smooth family of NC pairs of general type, then you can form the relative log canonical model. So again, this means you just take the proj of this canonical ring, but instead of taking global section, you just push forward via this map. So this will be a semi-log canonical pair, even log canonical in this case, with ample kx plus b over t. But the nice thing is that the fibers will be the log canonical models of the fiber of the original family. So in other words, forming the log canonical model commutes with base change. And this is certainly a very, very desirable property to have when you are dealing with, when you're considering moduli of stable pairs, which are obtained by taking the log canonical model. And remark, as all these fibers are canonical models themselves, they are in particular SLC, so they are S2. So this is a manifestation of this equivalence, if you wish. Any questions about this part?
There are no questions in the chat for now.
Okay, very well. All right. Oh, I'm going very fast. Okay. All right, something about, so what about positive and mixed characteristics? Because these questions can, you can ask about invariance of plurigenera in positive and mixed characteristics as well. You want to construct moduli of higher dimensional varieties in positive and mixed characteristics as well, especially if you're interested in arithmetic applications. So the situation, unsurprisingly, is a bit different. So it's well known that Hughes' theorem, as stated, can fail. So there are examples of families of surfaces, smooth projective family of surfaces, where the genus jumps. So the first plurigenera jumps. And the first to give such examples was Lang in '83 by considering super singular and Rick surfaces. Katsura and Ueno gave examples with elliptic surfaces, and much more recently, Su showed that this can happen even in the canonically polarized surface case. However, if you're interested in, something that you can see about these examples, if you read through their construction, is that maybe the first plurigenus is not invariant, but if you consider only the sufficiently divisible m, so all the m that are multiples of sufficiently divisible number, then those plurigenera are actually invariant. And for moduli application, this is really all that you need, because you're not interested in saying that the log canonical ring you don't really want to say that the log canonical ring commutes with restriction, but it's enough to say that a Veronese subring of it does. And so this asymptotic version is really what you need. And so you might ask, so is this always true? So if you have a nice projective family of integral normal pairs, so nice here can mean maybe log smooth with KLT fibers or canonical singularities, then is it true that the invariance of plurigenera holds for all M sufficiently divisible? So I named this, I refer to this question as AIP, which stands for asymptotic invariance of plurigenera. Asymptotic meaning that we only consider those M's. And so there were some positive results. So for example, Bernasconi and Stigan and Egon and Hegbert show that this is indeed the case basically most of the time in for surfaces. However, it's not always the case. So the answer in general is no. And more precisely, you can have the following, there are the following examples in any characteristic P. So we can have projective families of minimal surface pairs of codara dimension 1, such that asymptotic invariance of plurigenera fails. And even more surprisingly, maybe, is that you even have families of general type threefolds, such that asymptotic invariance of plurigenera fails. And so first of all, note that, so this is really not a sort of a phenomenon that only happens in small characteristics. So this happens for all P. So this is not a rare pathological phenomenon, but it's something that you really encounter. And as you will see from the construction, in both of these cases, the log canonical divisor is semi-ample. So it has a very, very nice positivity property. And nevertheless, plurigenera still manage to fail to be invariant, even in this asymptotic version. All right, so I want to give you, I want to show you how to construct both of these examples. But before I do that, I need to recall this lemma, which is very useful to study extension of section of semi-ample line bundles. And we're going to be using this throughout. So suppose that you start off with a contraction with normal integral fibers from X to spec of R. So this is a projective morphism with connected fibers. I'm really thinking of it as a family of integral normal varieties. And then we take L to be a semi-ample line bundle on X. And so if it is a semi-ample line bundle, then it has its associated contraction, F from X to Y. Then the following conditions are equivalent. So we have asymptotic invariance of dimension of the spaces of M twisted sections for M divisible enough. This condition basically means that the restriction of F to the central fiber is itself a contraction. And if L is big, then we also have that both of these conditions are equivalent to YK being normal. So the proof of this, I mean, it's not really a sketch, but so 1 implies 2. This is clear because, I mean, if what is it? If every section of LM to the K, LKM on the central fiber can be extended to the total space, then it means that basically you can lift the Itaka vibration of the central fiber to the total space. But the Itaka vibration is indeed a vibration, so this F small k should be a contraction. For the reverse implication, note that if you write, you can use the projection formula, so H naught of L T to the M. Oh, sorry, maybe I should say something before. So since F is the semi-ample contraction of L, you have that L is Q linearly equivalent to the pullback of A, where A is an ample Q divisor on Y. Then you can use, you can express H naught of xt lt m. You can use the projection formula here and compute it as H naught of yt ft lower star of oxt tensor ozt m. Sorry, that's not c, that's y. Yt mat. So this is just the projection formula, right? But then if you know that the central fiber, the morphism restricted to the central fiber is a contraction, then you can rewrite this as ht oyt mat. Right? I mean, time factorization commutes with base change. So f on the generic fiber is certainly a contraction, and by hypothesis we know that it is also the case on the special fiber. Very well, but then if you take m divisible enough, so in particular large enough, then this is just the Euler-Poincare characteristic of yt mat, and this is invariant in smooth families. Sorry, it's invariant in flat families. Okay, so this shows the other implication. So again, for the same reason as 1 implies 2, we have that 1 implies 3, because I mean we start with something with normal fibers, and the image of the Itaka fibration of something normal is normal again. So if by 1 we can lift the Itaka fibration from the central fiber to the total space, then yk will be indeed normal. For the reverse implication, one can consider f sub k, and you can take its time factorization. So gk hk, and now this will be a contraction, and this will be this will actually be a universal homeomorphism. Which is also birational. Okay, and now it's a consequence of Zariski's main theorem that if you start with a normal variety, so yk in this case, then every birational universal homeomorphism has to be an isomorphism. So this is the definition of a weakly normal scheme, and a normal scheme is a weakly normal scheme. So this is a consequence of Zariski main theorem. So HK has to be an isomorphism. And so FK coincides with this time factorization. So this in particular means that 2 holds. Is that okay? Any questions?
Not for now, apparently.
Okay. All right. So, oh, sorry.
Can you please repeat why the universal homeomorphism is an isomorphism? Yeah,
so I mean, this is a general thing. So this is the Zariski main. This is one of the many forms of Zariski's main theorem. So, like for example, in EGA is stated exactly like this. The reason HK is a universal homeomorphism is that while we don't necessarily know that FK is a contraction, we know that F is a map with a connected fiber. a morphism with connected fibers. And so F sub K will also be a map with connected fibers. So you can be more precise about this, but if you think about it, this forces these to be to have connected fibers too. So because otherwise, if it didn't, then FK would not have connected fibers either. Is that okay?
Marta says yes.
Oh, okay.
Maybe you cannot see her.
Yeah, no, I can't see anything. All right, very well. So, okay, let's talk about the first example. So this is due to myself, and the ingredients are as follows. So we start with an elliptic curve over the DVR, so or a family of elliptic curves, if you prefer, smooth family, such that there exists M, a non-trivial p-torsion line bundle, such that it specializes to the trivial one on the central fiber. So this can always be achieved. For example, if you are in equicharacteristic, you can take an ordinary elliptic curve and degenerate it to a supersingular one. Or if you are in mixed characteristic, this always happens after possibly extending the DVR. And then we take P1 of R with N being the hyperplane bundle and ST being their homogeneous coordinates. It's homogeneous coordinates. And then we let Z be the product, L be the product of M with N. And then we take sigma, this section in the pth power of L. So here 1 is just the sort of the tautological section, the only section in M to the P. And yeah, SP minus 1 times T is just degree P polynomial. And so with this data, one can form one can take the pth root of sigma and obtain a P cover, and we normalize it. So we take the normalized P cover, and then we have an induced morphism from X to P1 of R. And the picture is as follows. So if imagine this is our DVR. So this is the generic point, and this is the closed point. And then we have a family of surfaces here, X. And you can check, this is a local computation, that it is actually smooth over R. This is a nice projective family of surfaces. And then we have our morphism F to P1. And on the generic fiber, everything is fine. This is just an elliptic fibration. It will have two multiple fibers over 0 and infinity, but besides that, there's nothing much going on. On the central fiber, instead, something strange happens. You see, since you took M that becomes trivial on the central fiber, when you take this cover, on the central fiber, this doesn't really give you, I mean, this is already a pth power, so you're not really taking any root here. So you're just taking a root of, say, in the coordinate s not equal to 0, you're taking the pth root of t. So what you're doing here is you are extracting a pth root of the coordinate t here in P1, so you're factoring through the Frobenius. So you see, this map FK bar is a contraction, but then you have a finite morphism. In other words, the time factorization of the central fiber is no longer, I mean, FK is no longer its time factorization. And so the fibers here will not be really elliptic curves, but will be sort of pth thickenings of elliptic curves. All right. And so now, how do you conclude? So if you note KXT, so the Kodara dimension of this family is actually minus infinity. However, you can get something of Kodara dimension 1 by letting B be the sum of AI f pullback of PI, where PI are just points are points of P1, and AI are positive but small enough. Then you will have that if you consider this family, XP over spec R, this is now a family of terminal pairs. Kx plus B is semi-ample of Kodara dimension equal to 1, and F is its Ithaka vibration. So, in particular, by the lemma that we proved a moment ago, asymptotic invariance of plurigenera here fails. All right. Also, it's you can show using asymptotic Riemann-Roch that this jump in the plurigenera is proportional to, let me write it. So the jump in plurigenera is proportional to the rank of Fk lower star Ox. Okay. So, and I mean, maybe you guessed it already, but this construction really doesn't need P. You can take P to the E here and repeat the construction. Everything works fine. What you get is that the rank of this coherent sheaf becomes bigger and bigger. So you can have arbitrarily large jumps in plurigenera for any M sufficiently divisible. So this is yeah, you cannot save anything basically. Yeah, asymptotic invariance of plurigenera fails in the worst possible way. All right. So the second example is due to Collar, and it's obtained starting from the first one. So we take X to spec R, the family from the previous examples, and we let lambda, a positive divisor, an effective divisor on X, such that the fibers now are Calabi-Yau and terminal for all T in spec R. Basically, lambda is obtained as B, but you take less points, or you diminish the coefficient even more. And then we let L be the log canonical divisor of the previous example, so Kx plus B, so the one that induces this very strange vibration. And then we let Y be a P1 bundle over X. So here A is just like any ample line bundle, doesn't matter. And this P1 bundle will have two sections, which I denote by X0 and X infinity. X infinity is a movable section. As a divisor, it is actually semi-ample, and it's the one that induces the contraction of X naught down to the cone over X. While instead X naught is fixed; it doesn't move. There's negative normal band. Very well, and then we let lambda y and ly be the pullbacks of respectively lambda and L to y. And we take X prime infinity Q linearly equivalent to 2X infinity effective Q divisor, and Ly prime Q linearly equivalent to Ly, again, general enough, so that the singularities are not too bad. And then if you set D equal to this divisor here, you can check that this family becomes it's a log smooth projective family of PLT threefold pairs, with X naught being the PLT center. And you can verify that KY plus D is actually Q linearly equivalent to X infinity plus Ly. So in particular, it's semi-ample. Both these divisors are semi-ample, so their sum is. And in Sitaka vibration, we can actually draw a picture of it. So if you think a moment about what it should happen according to this decomposition, so we have our family of surfaces that we started from before. And then we are taking this P1 bundle. Right. Okay, so this is my Y, and the section that I'm drawing here is the fixed one, X naught. Okay, and now if you think from really numerically, what should the Itaka vibration of this do? So X infinity is just gives the map that contracts this section to a point, and everywhere else is an isomorphism. Ly comes from is the line bundle that comes from the previous example. So what this gives is a map that is what the map that this gives on X naught will be the vibration of the previous example. So when we put this all together, what we end up is with a contraction to a family of trifolds that looks something like this. So again, as I mentioned, you're contracting this section to a curve, and the contraction is nice on the central fiber, on the generic fiber. So these fibers contract to this curve, this section contract to this curve with an elliptic vibration. But on the special fiber, instead, you again have this P thickening of these elliptic curves. So again, it's a computation, but you can show this that what's going on here is basically that this admits again a non-trivial time factorization through something that is universally homeomorphic to it, but the only difference is that on this curve, this map acts like the Frobenius. So this is an important consequence. So we have that if you let YC be the canonical model, then you will have that YCK is non-normal. So again, by the lemma before. So in particular, it's not S2. So this is something new, right? Because if you remember from the definition of stable families, this pair being SLC was equivalent to the fibers being SLC. This is A prime, if and only if A double prime. This is no longer true now. This pair it is SLC is actually even LC, but the central fiber not being S2 is not even SLC. And so this has some strong consequences because it turns out that the functor of stable families in the second sense, so the one where stable means that this condition is satisfied, this being SLC is satisfied, this is still separated. But so what then it means is that this functor cannot be proper because this pair is the only possible limit that you can admit working with stable families in this sense. But it is not a stable pair itself. So you get something that is you get a non-proper functor now, and this is a bit annoying because typically one wants to work with modular spaces that are compact. Okay, so on the positive side, instead, we have the following result, which assumes a resolution of singularity. So if you have suppose that you have a projective family of normal integral KLT threefold pairs, and suppose that you are in characteristic greater than 5, and assume that one of these conditions holds, so either the central fiber has Neff-Lock canonical divisor, or X is Q factorial, and every non-canonical center V of this adjoint pair, which is contained in the diminished stable base locus of Kx plus V, is horizontal over R. So this is a technical condition, but if you require the family to be log smooth, it is automatically satisfied. I will tell you more about this in a moment. Then asymptotic invariance of plurigenera holds. So this is a little bit bad. I mean, this is sort of it tells you that if you remember, the family of threefold that we constructed before was not KLT, was PLT. That it had a divisor with coefficient 1 in the boundary. And so the nice thing is that it turns out if you consider just families of KLT things, then everything should be fine. So the proof is not too difficult. I can sketch the argument for you. Now, so we have this family of threefolds, and let's assume that we are in the second hypothesis. The first one is, I mean, you can reduce. We will reduce to a situation where the first one holds. So the point is, you start with this family of threefolds, and then you can run an MMP. So we cannot run MMP for fourfolds. These are fourfold in general, but we can when they are over a DTR. So this is a Kx plus B MMP over R, and this is a result of Hecon and Vitasek. And so because of this condition, so the reason we have to put this condition, this is really essential. This implies that rho t is kxt plus bt MMP for all t in spec R. So this relative MMP is actually an MMP in family. Okay. So MMP, the MMP preserves, asymptotically at least, preserves the number of pluricanonical sections. So it's enough to show asymptotic invariance of plurigenera for the family of minimal models X bar B bar over spec R. Now, by results of Cascini and Tanaka and Vitasek about semi-ampleness, relative semi-ampleness, we can say that Kx bar plus B bar is semi-ample. These results basically tell you that if you have something over a DVR in positive or mixed characteristic and you have a line bundle, then relative semi-ampleness is equivalent to semi-ampleness fiber-wise. So in a certain sense, semi-ampleness in positive and mixed characteristic behaves better than in characteristic 0. And in this case, we can apply these results because this is now a family of KLT pairs of general type dimension 3 and which are minimal models, and so we can apply the Kohn theorem, and so we have semi-ampleness on generic and special fiber, and then we can put it all together by these results. Very well. So now, if it is semi-ample, we can take f from x to y, the semi-ample contraction, and remember we need to show that fk is a contraction itself. Okay, now what you can do is consider this standard exact sequence. And then push it forward with f lower star. So This is a contraction, so you can apply projection formula here. Then here it's, well, the thing we are interested in. And then you have the first direct image. And this map here is induced by multiplication by pi, uniformizer of the DVR. So it is certainly enough to show that the first direct image here vanishes. And by upper semi-continuity, we can actually show something even more special. So the direct image on the central fiber is 0. And the reason this holds is that if you look at the Stein factorization, so let's say this is GK and this is HK. Then it basically follows from the definition that this map here is the canonical model of XK VK. All right, and in particular by the Grothendieck spectral sequence, the vanishing of this direct image is equivalent to the vanishing of the direct image through GK. But and now the reason this thing vanishes now is because YK has KLT singularities. And by a theorem of Arvinson, Berlusconi, and Lassini, when P is greater than 5, KLT singularities are rational. Which is exactly, I mean, which means exactly this, that this local, this relative, these higher direct images, they are all 0. All right. So, since I'm almost out of time, let me conclude with a couple of questions that I think they are interesting. I mean, or natural, at least. So the problem is we found out that the moduli functor of stable pairs in characteristic P, or mixed, is basically almost never proper once the dimension is greater or equal than 3. So we would like to fix it. One way is saying, which is sort of the maximalistic approach, we say, okay, let's enlarge the category of stable pairs in order for us to allow for these more general schemes that appear in the boundary. So the natural thing to do in this, I think, is going as follows. So we say that a scheme X is quasi-deminormal if it is reduced S1 at most nodal in codimension 1, and the deminormalization morphism is a universal homeomorphism. So this is basically the non-S2 version of a deminormal scheme. It's very, very close to a deminormal scheme because well, I mean, it's homeomorphic to its deminormalization, but yeah, it's not. It need not be S2. So with this definition, you could say, oh, okay, let's try to enlarge, define the category, define the functor of quasi-stable pairs by redefining stable pairs by just replacing demi-normal with quasi-demi-normal in the definition. And then we get a functor of quasi-stable pairs dimension n and volume V. And the question is this guy proper? And the good news is that I mean, it's in general it's difficult. I mean, it's difficult to say something in any dimension because we don't know semi-stable reduction in characteristic P for like things that are of dimension greater than 1. So if you want to show that the stable reduction holds, you should first show the semi-stable reduction hold. But I think that we have no idea about how to do that. However, you can show that first of all, this takes care of Collar example because this definition is exactly tailored to that, and you can also show that if you assume semi-stable reduction, so if you assume that you can always get a semi-stable family, then if you take the relative canonical model, you will get a family of quasi-stable pairs. So if you're willing to believe semi-stable reduction, this takes care of the problem of the lack of properness. However, there is another problem, because if you allow this kind of non-S2 schemes, you quickly realize that these are actually, they do not form a bounded class. So the corresponding moduli functor, albeit being valuative proper, would be not of finite type. This is also something that you really, at least I don't particularly like. So the example of unboundedness is basically, we already saw it. So we take this surface, everything is over a field now. So we take an elliptic curve times P1, and then we take the morphism phi E, which is first you project onto P1, and then you follow up with a P to the eth power of the Frobenius. So we have that this morphism is induced by a base point free linear system, which I call VE, which lives inside this space of total sections. And then, as before, we construct our P1 bundle. Again, A here is any ample line bundle. We have mobile and fixed sections S infinity and S naught as before. And then we take M to be sufficiently divisible, and we let big phi sub E be the morphism induced by the pullback of VE to the P1 bundle Z, and then we tensor it with this semi-ample linear system. So I'm taking M sufficiently divisible here, so that this guy gives me actually the contraction to the cone. And what you find out is that the images ZE do not form a bounded family. So the picture here is exactly as before. So we are taking this section, and then we are contracting it to a curve. But then we are following it up. So we have this sequence of homeomorphic schemes, but what changes here is that on this curve you have iterates of the Frobenius. So, and this is ZE. Okay, so these are all strictly quasi-demi-normal. So neither of them is S2 once E is greater than 0. They all have the same normalization, which is this one, and but you can show that they cannot form a bounded family. One way of saying this is, for example, if you localize this generic point, and you look at the local cohomology, you can compute it using this resolution. And you will see that it's unbounded. So it's like it has assumed countably many values. All right. So maybe we have a fix for properness, but on the other hand, you are including sort of too many schemes, and so you might be lacking boundedness. There is another approach, which is sort of the dual one. So you, instead of enlarging your moduli functor, you can sort of restrict it, and then hope that these very nasty schemes do not show up. So a question that I think it's natural and interesting in this case is the following: to define S bar KLT3V inside the functor of quasi-stable pairs to be the subfunctor of three-dimensional quasi-stable pairs XB, which are limits of stable KLT pairs. So they admit sort of a smoothing, although it's not really a smoothing, but yeah. I mean, you can deform them to a KLT pair. And now the question is, if you have such, oh, sorry, there's a typo here, because the answer to this question is clearly no. But what I really want here is S3 KLT. So if you have something that is a limit of KLT pair in characteristic greater than 5 in dimension 3, then is it true that is it an S2 scheme? So we hope that these quasi-normal pairs do not actually show up when one closes the KLT locus. And this is something that I suppose you could attack with techniques similar to the ones that I used to prove that theorem about invariance of plurigenera for KLT threefold pairs, but this is more difficult. So one needs to be more careful about this case, because we are not really dealing with a family of of integral varieties. Anyway, this is all that I wanted to say, and thank you very much for your attention.